Yes, my dear students, whomsoever is listening my this lecture, I am going to talk about emerging technologies in renewable energy sources, basic and early design of solar distillation. This is part 1 of emerging technologies. I am Dr. Anil Kumar Tiwari from the Department of Mechanical Engineering, National Institute of Technology, Raipur, Chhattisgarh. My area of working is solar thermal applications. The possible renewable sources are solar energy, wind energy, hydropower energy, biomass energy, and geothermal energy, in which my lecture is confined to the recent trends of energy savings by solar thermal different applications. The possible technologies in solar thermal applications are distillation of water for the purification using solar energy, active or passive techniques, or by humidification and dehumidification. For building, heating and cooling, and ventilation induced by solar energy using trombe wall, solar metallic wall, solar chimney, transpired wall, etc. Solar water heating applications as well. Industrial discharge of chemical water and byproduct is one of the reason of sources of water pollution. Another one is discharge of poorly treated or untreated sewage. The third one is the surface runoff containing pesticides. The fourth one is surface runoff from construction sites and farms. The fifth one is the discharge of contaminated water used for industrial process. And the sixth one is the excess nutrients added by detergent or fertilizers. The effect of water pollution are normally infectious. There are various waterborne diseases. The bacterial infection leads to typhoid, cholera, paratyphoid, then bacillary dysentery. The viral infection normally induce the infectious hepatitis, that is known as the jaundice, and the protozoal infections are amoebic dysentery, etc. The need of drinking water. Our Mother Earth has plenty of water, but limited resources of fresh water is there. 1.8 billion people will suffer from water shortage by 2025. The economic growth is the most important driver of the future water scarcity. The water saving and desalination are the tools to face the water crisis. Now, why distillation? The permissible limit of salinity in water is 500 ppm, sometimes 1000 ppm for special cases, according to World Health Organization. While most available ground and surface water has this, there are 5000 ppm or even more which is available to us. One of the methods to reduce salinity is distillation. Water purification can be achieved through various techniques. Essentially, there are three primary methods for producing safe drinking water. Number one is membrane technologies. We use in our home, the RO system is the same. Number two is the distillation process. Number three is chemical approaches. Solar distillation method is an easy, small scale and cost-effective technique of providing safe water at homes or in small communities. It is one of many processes that can be used for water purification. The process requires energy input as heat, and the solar radiation can be one of the source of the heat energy. As can be seen, when water is heated by solar radiation and turns into vapor, leaving salt behind, and when the surrounding air cools, leading to condensation, the resulting water droplets are collected is our distilled water. Process of getting fresh water from saline or brackish water is distillation, and using solar energy for the same is solar distillation, which is done easily and economically. As far as classification of solar distillation is concerned, it is of two types: passive solar still and active solar still. In case of passive solar stills, once again there are two classifications, either conventional single slope or conventional double slope. Whereas in case of active solar still, once again there is two classifications: high temperature distillation or nocturnal distillation single slope. Now, as far as conventional double slope is concerned, it can be either symmetrical or non-symmetrical, whereas in case of high temperature distillation, it can be either auxiliary heating or using collectors for heating purpose. It produces the advantages of solar distillation. It produces pure water. No conventional energy source is required. No skilled operator is required to run the unit. Local manufacturing and repairing is possible. Low investment requires. It can purify highly saline water even. Now, the working of the passive single slope conventional solar distillation, you can clearly watch in the figure. As you can see that when the water is heated, vapor goes to the condensing cover, touches the lower temperature condensing cover, get condensed there, dribbled under the surface because of the gravity and get collected. Solar radiation is absorbed primarily by the black basin and it is then converted into thermal energy. Water vapor condenses on the inner side of the glass cover and the distillate flows by gravity into the water collection tray. The distilled water subsequently flows into the freshwater tank via a drain tube. This is the way how we collect the distilled water. Now, there are heat and mass transfer involved within the solar still, which makes it possible to collect the distillate output. There are two types of heat transfer. One is external, which is outside from the distillation unit to the atmosphere, and one is internal. As far as external heat transfer is concerned, it is conduction from basin to ambient, there is convection from glass to the ambient, there is radiation from glass to the ambient. Now, as far as internal is concerned, there is evaporation of water from basin to the glass, there is convection heat transfer from water to the glass, there is radiative heat transfer from water to the glass. Internal heat transfer is responsible mainly for the transfer of water from basin to the glass. External heat transfer is responsible for the heat loss from the glass to cool the glass so that inside water vapor can be condensed. Now, use of distilled water is industries for industrial processes, in hospital and dispensaries for sterilization, it is used for radiator and battery maintenance, in laboratory for analytical work, and nevertheless for drinking purpose, marshy and coastal areas to get fresh potable water for survival in the community. Now, the drawbacks of the solar distillation. Low production output is one of the drawbacks, approximately 2 to 3 liter per meter square per day under hot weather condition. For more output, larger still area is required, and it is also weather related dependency. So, if the weather is not favorable, there are risk of not getting the yield. If the weather is worst, there are risk of getting damaged the solar still. The third drawback is effect of meteorological parameters, the total dependency on the meteorological condition. The output of solar distillation highly affected by climatic parameters such as solar radiation, ambient temperature, and the wind velocity. The output is more in hot climate, with comparison to the cold climate. As can be seen for simple single slope solar still, the sun's radiant heat is absorbed by a basin and subsequently transferred to the water within, causing it to heat up and eventually evaporate. This vapor then undergoes condensation upon coming into contact with a cooler surface, that is condensing cover, solar radiation permitting glass, which is at a lower temperature compared to the water as the glass inner surface. As a result, it accumulates as distilled water, and this process effectively separates the water vapor from any dissolved impurities or substances. The condensed water emerges as pure and distilled water. The primary determinant influencing the yield obtained from a solar still is the temperature difference between the water in the basin and the glass cover. Normally, it is said as Tw minus Tg. Tw stands for temperature of water, Tg stands for temperature of glass. Greater this temperature difference, the greater will be the result as an increased distillate output. There are two types of solar still, as I have told you earlier as well. The passive solar stills, in which solar thermal energy directly heats to the water of the basin. In case of active solar stills, the solar energy directly does not heat to the water of the basin, whereas some other arrangement is made where solar energy received in basin, additional energy consuming some sources are needed. As in case of single slope solar still, as evident, the construction of a single slope solar still is a straightforward, simple process. It involves assembling a fiber reinforced plastic, normally we call FRP, body for maintaining a good insulation with an inner surface coated black paint capped by a transparent glass top cover, which permits solar radiation to get in and also provide an enclosure for the vapor not to run away. The optimum orientation of the solar still is crucial to harness the highest amount of solar radiation, typically aligning its inclination with the latitude of the specific location where the solar radiation is likely to be kept. In case of double slope solar still, when single slope solar still faces to a certain direction, normally it is south for the countries or places on the northern hemisphere like India, double slope solar still is kept in east-west direction to receive solar energy throughout the day. As can be seen in the figure, it is kept on east and west direction. The working is same as of single slope solar still. In double slope solar still, it is important to mention that when the east side acts as a source of solar energy input, the west side acts as a condensing surface in morning hours and vice versa in case of evening. In winter, the single slope FRP still gives better yield than the double slope stills, but in summer the double slope stills give better yield than the single still. As far as annual reproduction is concerned, the double slope is better. In summer, the path of the sun is almost over the head, unlike winter, when the path of the sun is declined to the south direction. Therefore, in summer, the double slope is better. Another type of solar still is hemispherical solar still, when the radiation permitting cover is having a hemispherical shape. Hemispherical solar still is a remarkable innovation in a field of solar distillation, and water purification. Its design mimics the shape of a half sphere, which not only makes it aesthetically unique but also highly efficient in harnessing solar energy as well. This ingenious device consists of a curved concave basin with a transparent cover. The basin is usually coated with a dark heat absorbing material to accelerate the water heating process. Here is how it works. As the sun's rays penetrate the transparent cover, they heat the water within the basin. This heat causes the water to evaporate, leaving impurities and contaminants behind. The vapor then condenses on the inner surface of the cover and collects as pure distilled water. This process effectively separates fresh water from any dissolved solids, making it a valuable tool in areas where clean drinking water is scarce. Hemispherical solar stills are particularly efficient because of their unique shape, which allows for maximum exposure to sunlight, whatsoever the path of sun is, whatsoever the season is, throughout the day, throughout the year. They are a sustainable and eco-friendly solution for addressing water scarcity issue in arid regions, offering a simple yet effective way to obtain clean and safe drinking water from readily available solar energy. The solar stills basin is crafted from mild steel or some other material, with its surface coated in black paint to augment its ability to absorb solar radiation. Additionally, a water drainage system is securely affixed along the inner perimeter to collect distilled water. The top cover of the still consists of a transparent acrylic sheet of hemispherical shape. The saline water is filled in the solar still up to a depth of 0.05 meter. The spherical solar still is a sphere. It comprises a circular basin crafted from aluminum and an absorber plate coated with black paint to maximize solar radiation absorption from all the directions, even the solar radiation which is reflected from the ground. A typical absorber plate measuring 0.4 square meters in area and 0.61 meters in diameter is employed for containing saline water within the basin. The circular basin is positioned in the middle of the spherical rings at a height of approximately 0.28 meters, a typical design relative to the total height of a solar still, which is 0.68 meters. The system has demonstrated a maximum efficiency of the order of 22% under the climatic condition of Coimbatore when a research was held in India. The same varies with season and location. A simplified mathematical model of a spherical solar still, which applies to any solar still, is shown. Please note that real-world models can be quite complex, taking into account the various factors such as heat transfer, mass transfer, and environmental conditions. This is a basic model to give you an idea. Particularly in describing this model, the assumptions are: number one, the spherical solar still is a perfect sphere. Number two, the solar radiation is uniform across the entire surface of the sphere. Number three, the system is in a steady state operation. There are nomenclatures like R is the radius of the sphere in meters, A is the surface area of the sphere, which is nothing but 4 pi r square in square meters, I is the solar radiation intensity on a horizontal surface in watts per square meter, alpha is absorptivity of the inner surface of the sphere. It is dimensionless. Then Tw is the temperature of the water inside the sphere in Kelvin, whereas Tc is the temperature of the cover in Kelvin. Capital U is the overall heat transfer coefficient in watts per square meter per Kelvin, and m is the mass flow rate of water vapor in kilogram per second, whereas Hf is the latent heat of vaporization of water in joules per kilogram, and rho is the density of water in kilograms per cubic meter. Energy balance. The energy balance for the spherical solar still can be expressed as I, which is solar insolation, into capital A, which is the area receiving the solar radiation, into alpha, which is the absorptivity of the surface which is absorbing the solar insolation, which is equal to U, overall heat transfer coefficient, into A, area which is receiving the solar radiation, into temperature difference of water to cover. The mass balance for the spherical solar still can be expressed as the m will be equal to rho into area into heat transfer coefficient into temperature difference upon the latent heat of vaporization. This equation represents the rate at which the water evaporates from the surface of the water inside the sphere. There can be triangular pyramid solar stills, which if you see and watch precisely, you will find that the area increases in case of triangular pyramid solar still. In pyramid solar still, top cover is in the shape of pyramid, triangular pyramid, or it can be square pyramid as well. And the major advantage of pyramid solar still over conventional single slope solar stills are, in a conventional solar still, the still must be positioned so that its inclined surface directly faces to the sun and needs continuous adjustment as the sun moves across the sky to capture maximum solar radiation throughout the day. Conversely, in case of a pyramid solar still, such adjustments are not required. Compared to the single slope solar still, the pyramid shaped solar still experiences less shading of its side walls on the water surface, which reduces the obstruction of solar radiation. Consequently, for the same basin area, condensation in the pyramid shaped solar still is higher, as the condensing area in the pyramid shape is greater. This presents an additional advantage. Another type is the multi-wick solar still. As can be seen in the figure, there are wicks lying on the basin. The amount of water in the basin plays a significant role in determining the heating rate, and in other words, evaporating rate. In the case of a wick type solar still, the water mass in the basin is instantaneously kept minimum, essentially in the form of wetness on the wick. This deliberate approach accelerates the heating process, resulting in faster evaporation and consequently an increased production rate of potable water. This stands as a major advantage of wick type solar stills. In multiple wick solar stills, multiple layers of cloth wicks are stacked on the top of each other. One end of the jute cloth sheets is submerged in the water reservoir, while the other ends are spread across the base of the solar still. To ensure optimum capillary action, it is essential to thoroughly wet the jute cloth before laying it out on the solar still's base. To harness the maximum solar radiation, the surface is angled precisely, allowing the jute cloth to draw water from the reservoir through capillary action to the upper end of the inclined surface. A glass cover is then positioned over the unit to facilitate the condensation of vapor on its inner surface. Multi-wick solar stills exhibit superior performance and are cost effective to construct, resulting in an improvement of 20% to 45% compared to single slope solar stills. Another one is the concave wick solar still. as the figure shows the shape of concave basin. To enhance the performance of the wick-type solar still, the concave wick-type solar still has been introduced. The concave shaped wick basin effectively increases the surface area for evaporation. The productivity or yield of the concave wick solar still reaches 4.1 liter per day per meter square. Furthermore, it has demonstrated impressive maximum instantaneous system efficiency of 45% and a daily efficiency of 30%. Another improvement is inclined wick type solar water distillation system. As can be seen in the figure, to ensure a consistent flow rate of water through the wick, the inclined wick type solar still has been introduced. This system can be adjusted to an optimum inclination angle to capture the maximum solar radiation. When maintained at this optimum tilt angle, the performance of the inclined wick solar still surpasses that of traditional wick type solar stills. Tilted wick solar still with flat plate bottom reflector. The solar still comprises several key components: a transparent glass cover, bottom insulation, a flat plate bottom reflector, and an evaporative wick. The flat plate bottom reflector, crafted from highly reflective materials, extends from the lower edge of the solar still. Optimum daily water yield occurs under specific conditions: a rectangular inclination of 50 degrees during the summer solstice, 30 degrees during the spring and autumn equinox, and 20 degrees on the winter solstice. The increase in daily water yield is most pronounced during the summer solstice at 25% and least during the winter solstice at 10%, when a bottom reflector is incorporated into the design. When the reflector is inclined at 35 degrees, the average daily water yield over 4 days increases by approximately of the order of 13% compared to the conventional tilted wick solar still. Then there is a conical solar still. As can be seen by the shape, the solar still features a circular base made of galvanized iron measuring of the order of a typical dimension 0.8 meters by 0.8 meters and a cone with a height of 33 centimeters. To enhance solar absorptivity, both the sides and the basin are covered with 0.7 mm thick galvanized iron to collect the distillate, which is painted black. Additionally, a transparent acrylic cover with a thickness of 0.5 centimeter is securely affixed at a 31-degree angle along the circular side of the still. This cover allows solar radiation to reach the basin, serving as both a condensing surface for potable water and a mean to harness solar energy simultaneously. This type of solar still is used inside the sea when boat is far inside the sea. It's worth noting that the conical solar still demonstrates higher productivity in comparison to the conventional single basin, single slope solar still. If the conventional version has similar dimensions of 0.8 meters by 0.8 meters for the basin and features a depth ratio of 70 centimeters to 10 centimeters for the higher and lower walls respectively. And for comparison, both the conical and conventional solar stills are constructed using the same material. Another one is the active one. Solar still coupled with flat plate collector. A solar still coupled with a flat plate collector is a combination of two solar technologies: a solar still and a flat plate solar collector which heats up the water. This hybrid system is designed to harness solar energy for both water purification and generation of hot water as well. In this design, a solar distillation system is integrated with a flat plate collector to preheat the water before it enters the solar still, effectively expediting the evaporation and condensation process. As a result, the average daily output of distilled water has been determined to be 24% greater than that achieved by a basic single basin solar still. Solar still coupled with parabolic concentrator, the same case. In this design, solar distillation system is coupled with parabolic concentrator to heat the water prior to sending it to the solar still. Similar as mentioned in previous case, the productivity increased and averaged by 18%. Solar still coupled with evacuated tube collector. All these examples are of active solar stills. Convection heat loss due to air movement inside the collector can be significantly reduced by maintaining a vacuum between the top glass cover and the absorber of a flat plate collector. The optimum daily yield has been obtained as 3.9 kg with energy and exergy efficiencies as 33.8% and 2.6% respectively during typical summer day of a typical dimension. The solar insolation received on the still's surface depends on factors like location, day, time of day, weather conditions and the angle of the cover slope. It can be calculated using the formula Q is equal to area into insulation into efficiency of the collector. Thank you.